Heat in dielectric materials is carried by phonons. Phonons are nothing more than quantized thermal vibrations dealt with in a periodic material by the Bloch theorem that allowed us to solve the eigenstates for electrons in a periodic material. So if one plots the energy of a thermal vibration against their quasi-momentum k, one sees a band diagram very much like that obtained for electrons in a material, where this region out here corresponds to the Brillouin zone boundary. Now, phonons in these branches up here, the so-called optic modes, which correspond to localized vibration, have, as you can see from the gradient of these curves, a small group velocity. The same is true for phonons out near the Brillouin zone boundary. It's these long wavelength phonons here, this gradient here is the speed of sound, that predominantly carry heat in a material. For such long wavelength phonons, the scattering lengths are also generally quite long, perhaps hundreds of nanometers at room temperature. Now, in an electronic conductor, electrons, and in a semiconductor also holes, can also carry heat. If you recall in Chapter 7, we discussed how the low temperature specific heat of a material is linear in temperature if it is an electronic conductor, because of the predominance of this mode of heat conduction. So one very important application of nanostructuring for phonon density of states engineering comes about in thermoelectric devices. So the pictures on the left of the slide show a couple of examples of thermoelectric devices. Let me just illustrate the example of one, which is the thermoelectric cooler you may be familiar with. I believe you can even buy these in individual beer can cooling type devices. So these things look the following way. It's an electronic connection, and then up here a metal bridge shorting these two devices together. Here is a p-type semiconductor, here is an n-type semiconductor, and then a current is passed through the device like this. In the p-type semiconductor, the current consists of holes being swept towards the negative terminal of the battery. In the n-type semiconductor, the current consists of electrons being swept towards the positive terminal of the battery. Therefore, this junction at the top is being constantly depleted of carriers, both electrons and holes, and heat is being carried away from the top junction, with the result that this part becomes cold. Of course, conversely, this part becomes hot. And therein lies the problem. Devices that are good electrical conductors are usually often good thermal conductors, so the performance of these active thermoelectric coolers is spoiled by the diffusion of heat from the hot element back to the cold element. Panel B shows the same type of device, only there a thermal gradient is being applied in order to generate a current. So these devices will act as a way of converting heat energy into electricity. One approach to making devices that carry heat relatively poorly while still generating a heat gradient from electron and hole motion is to use heavy atoms. That's because this speed of sound here depends on the ratio of some elastic constant to density. And so if the material is made dense, the speed of sound is smaller and the thermal conduction is diminished. Unfortunately, not very much can be achieved simply by using semiconductors made of dense elements. And so another approach is to nanostructure the device so that it is heterogeneous on the length scale of the phonon wavelengths, but homogeneous locally on the length scales important to wave packets of holes and electrons. When you read papers on this nanostructuring, you will see quoted as a sort of figure of merit this parameter here, Zt. Z is just the ratio of the Seebeck coefficient squared. This is a coefficient that describes the thermo power of a material times the electronic conductivity divided by the thermal conductivity. If you do problem 14 at the back of chapter 9, you'll see that this has units of 1 over temperature, and so multiplying both sides by temperature then creates a dimensionless figure of merit for a thermoelectric device. This panel here shows the absolute cooling achieved as a function of current, here using bulk semiconductors, and then here nanostructured devices where significant enhancements in performance have come about from trying to engineer phonon scattering while maintaining the transport of electrons and holes.